Welcome back to linear algebra. In this video, we're going to be going through some ideas of matrix arithmetic. We've, of course, used matrices a couple of times already in this course. We developed the augmented matrix as a way of representing a system of equations and developed the elementary row operations to create row equivalent matrices, which is certainly a valuable tool and something worth looking at. When I talk about matrix arithmetic, I'm going to be looking at matrices in a completely different manner. Let me get my head out of the way and let's dive into some of these definitions. A matrix is a rectangular array of values. We call those values the entries of a matrix. If we talk about an m by n matrix, we are specifying a matrix that has m rows and n columns. And if we are talking about an m by n matrix called matrix A, typically the way we will denote the entries of matrix A is with first we name matrix A with a capital letter. We name an entry in matrix A with the corresponding lowercase letter. And the first entry is A sub 1, 1 for the first row, first column. A sub 2, 1 is in, I'm writing these the wrong way. A sub 1, 2 is in the first row, second column, all the way down to A sub 1n is in the first row, nth column. When I write down the entries in a matrix, I tend to go column by column, which is not the way that it's usually talked about. So I apologize if I get some things a little bit goofy in how I'm reading things from time to time. But A21 is the second row, first column. We have A22 all the way down to A2n. And then we can continue downward like this until we get down to the last row, the mth row. So we'll have A M1, A M2, all the way down to A Mn. And if you want to fill in that big empty space with a diagonal dotted line, I've seen that done before. There are some matrices where calling the diagonal into notice is valuable, and there are some matrices where it is counterproductive. For our purposes this semester, worrying about whether or not to include that is well outside of anything that I'm going to care about. For the sake of convenience, very often when we're talking about the entries of a matrix, instead of listing them all out, we will set up just in brackets A sub ij. And if we want to clarify, if it's not been announced somewhere else, that A is an m by n matrix, outside of that we can put a subscript m by n. So we know that I is going to range from 1 to m, and j is going to range from 1 to n. And with just that, we can establish everything we need to establish about the general form of the matrix. Of course, if we have specific values, then that's not so useful. But when we're talking about a matrix generally, that sort of thing tends to make our lives easier. Given two m by n matrices, which I'll name as A and B, we can add the matrices by adding the corresponding entries. One of the things I want to stress that is often missed if you've not dealt with matrices in the past is that I'm assuming that these are both m by n matrices. Or to put it more specifically, matrix A and matrix B have to have the same dimensions. If they do not have the same dimensions, we can't add them, even if they have the same number of entries. Right? A matrix with 2 rows and 3 columns has 6 entries. A matrix with 3 rows and 2 columns also has 6 entries, but not all of the entries in the 2 matrices will correspond to a matrix or to an entry in the other matrix. So we need to make sure that every entry in each matrix corresponds to exactly one entry in the same location in the other matrix, and we can only do that if the 2 matrices have the same exact dimension. Right. Talking about this symbolically, we can write this by saying that A sub ij plus B sub ij is equal to Aij plus Bij inside the brackets. And as a quick example, if I have a 2 by 3 matrix, 2 rows, 3 columns, say 1, 2, 3, 4, 5, 6. Yes, I'm very inventive about how I'm naming or how I'm coming up with these matrices. And another matrix with 2 rows and 3 columns, say 1, 2, 3, 4, 5, 6. We can add these together entry by entry. 1 plus 1 is 2. 2 plus 3 is 5. 3 plus 5 is 8. Whoops. 4 plus 2 is 6. 5 plus 4 is 9. And 6 plus 6 is 12. So the sum of these 2 matrices is 2, 5, 8, 6, 9, 12. If I have the row matrix 1, 2, 3, 4, 5, 6, and I have the matrix that is oriented with longer columns 1, 2, 3, 4, 5, 6, this addition is undefined because the dimensions of the 2 matrices are not the same. All right. So when we add matrices together, we add entry by entry, which means that if we add the same matrix to itself several times, we will add each entry to itself several times. And it would be nice to have a convenient shorthand for it. So if we have a matrix A and we have a scalar little k here, I can perform scalar multiplication by taking scalar k times matrix A, which is just multiplying each of the entries by that k. Right, so if I want to multiply, say, 1/2 times the matrix 2, 4, 8, 6, 12, 18, I will get 1/2 times 2, which is 1, 1/2 times 4, which is 2, 1/2 times 8, which is 4, 1/2 times 6 is 3, 1/2 times 12 is 6, and 1/2 times 18 is 9. Nothing too crazy happening there, I hope. And since we have matrix addition and we have scalar multiplication, that means that we can form a linear combination, C1 times matrix A plus C2 times matrix B. All right, so let's take 3 times the matrix 1, 2, 3, 4, 5, 6, minus 2 times the matrix 1, negative 1, negative 2, 2, 3, negative 3. Why did I do that? That's going to be confusing, but that's okay. If it's confusing, that means you have to pay closer attention. Notice here that we've got negative in the right column on the first row and the third row, but negative on the left column in the second row. All right, we should do this in 2 steps. Multiply 3 times the first matrix, multiply negative 2 times the second matrix. I'm going to write everything out in a really messy matrix. So we've got 3 times 1 minus 2 times 1. We've got 3 times 2 minus 2 times negative 1. We've got 3 times 3 minus 2 times negative 2. We've got 3 times 4 minus 2 times 2. We've got 3 times 5 minus 2 times 3. We've got 3 times 6 minus 2 times negative 3. And evaluating each of those one by one, 3 minus 2 is 1. 6 plus 2 is 8. 9 plus 4 is 13. 12 minus 4 is 8. 15 minus 6 is 9. 18 plus 6 is 24. All right. These operations should look very reminiscent of the operations that we can perform on a vector. And there's a reason for that, which I've hinted at previously. A row matrix and a column matrix well, let's see, this is one row and n columns. This is n rows and one column. These look identical to the row vectors and column vectors that we've been working with throughout the course. And in fact, they are. If we define a matrix as a two-dimensional array, and we compress one of those dimensions down to be just a single row or a single column, we get a vector. A vector is a one-dimensional matrix. And the fact that vectors are matrices is one of the reasons that vectors become so useful, or one of the reasons that matrices become so useful. Vectors, I hope you already are familiar with how useful they can be. Sure, we can set up the augmented matrix as a tool for working with a system of equations, but we can be more powerful in our use of vectors by defining matrix multiplication as successive dot products. So if I want to multiply matrix A times matrix B, we need to have matrix A an M by P matrix and matrix B as a P by N matrix, and then AB is going to come out M by N. All right. Going through and interpreting that, if you've not worked with matrices before, the number of columns in matrix A and the number of rows in matrix B must be the same. If they are not the same, you cannot perform multiplication. The number of rows in matrix A and the number of columns in matrix B are going to determine how many rows and columns there are in the result. Let's jump into a really quick example. I'm going to take some matrices that we've worked with before. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Notice that matrix A has 2 rows and 3 columns. Matrix B has 3 rows and 2 columns. The number of columns in the first matrix and the number of rows in the second matrix are the same. Then I'm going to successive dot products. I want to take the first row of the first matrix, pretend that it's a vector, and dot it with the first column of the second matrix. So I'm going to take vector 1, 2, 3 and dot it with vector 1, 3, 5. I will get 1 plus 6 plus 15, and I'll simplify that in just a moment. I find that it's easiest to continue onward successive dot products. Now take that first row and dot it with the second column, and that will be the entry in the first row second column of the product. 1 times 2 is 2, 2 times 4 is 8, 3 times 6 is 18. Then the second row of the first matrix, the first column of the second matrix, 4 times 1 is 4, 5 times 3 is 15, 6 times 5 is 30. And then second row and second column, 4 times 2 is 8, 5 times 4 is 20, 6 times 6 is 36. And then I can perform the addition. 1 plus 6 plus 15 is 22. 2 plus 8 plus 18 is 28. 4 plus 15 plus 30 is 49. 8 plus 20 plus 36 is 64. Our first matrix had 2 rows in it. There are 2 rows in the outcome. Our second matrix had 2 columns in it. There are 2 columns in the product. One of the craziest things about matrix multiplication that you haven't established in multiplication you've done previously is that matrix multiplication is not commutative. And in fact, very often, if you take the 2 matrices you are multiplying together and you write them in the other order, the product will no longer be defined. In this particular case, with this example, the matrix 1, 2, 3, 4, 5, 6, multiplied by the matrix 1, 2, 3, 4, 5, 6 is actually defined, although it's going to be very different. Because in this matrix, if I multiply the first row, dot the first column, 1 times 1 is 1, 2 times 4 is 8. Now, first row dot with second column, 1 times 2 is 2, 2 times 5 is 10. And then the first row dot with the third column, 1 times 3 is 3, 2 times 6 is 12. Second row, 3 plus 16, 6 plus 20, 9 plus 24. The third row, 5 plus 24, 10 plus 30, 15 plus 36. And when I add all of these together, I get a 3 by 3 matrix, 9, 12, 15, 19, 26, 33, 29, 40, 51. A completely different matrix than what I had before. All right. This is a strange way of thinking about matrix multiplication. It's a strange construction that we have here. So there should be a reason behind it, and luckily there is. Very specifically, setting up matrix multiplication like this gives us a really good meaning for taking a matrix, say a 3 by 3 matrix, 1, -1, 2, 2, -3, 3, 4, 5, -5, and multiplying that times a column vector, x, y, z. The rules of matrix multiplication. The number of columns in the first matrix, 3, the number of rows in the second matrix, 3, are equal. The result will have the number of rows in the first matrix, 3, the number of columns in the second matrix, 1. And look at what happens. 1 times x minus 1 times y plus 2 times z. 2 times x minus 3 times y plus 3 times z. 4 times x plus 5 times y minus 5 times z. If we take a matrix specifically the coefficient matrix that we talked about when we started looking at the augmented matrix and Gauss-Jordan elimination. If we take the coefficient matrix and we set it up as a matrix by itself, and then we multiply it by a column vector whose entries are the variables in our system, we're going to end up with a set of expressions which make up the left-hand side of a system of equations. A little bit later on, we will look at how we can take this, set it equal to another vector, and use that as a new tool for analyzing the solutions to systems of equations. For right now, I just want to make sure you can spend some time practicing these operations. So I would like you to take a look at one last example. Here I have a 3 by 3 matrix. Actually, we'll use the same 3 by 3 matrix. 1, -1, 2, 2, -3, 3, 4, 5, -5. And I'm going to multiply this by a 3 by 2 matrix. The very boring one that we've used several times, 1, 2, 3, 4, 5, 6. All right, I would like you to take a couple of minutes and work through that calculation, see what you get there. And I'll see you in the next video.